We very much welcome those watching the presentation at this moment. This paper addresses an amazing application of mathematics to electrical engineering problems, especially in power systems. The paper is about optimal preventive maintenance scheduling of power system generators using a discrete gyre optimization algorithm. The work is supported by ALGERIA Laboratory, Department of Electronics and Computer Sciences, USTHP. The work is done by Mr. Soufiane BELAGOUNE, Professor Nourdin Bali, Mr. Boussadia Baji, Professor Karim Atif, and Dr. Hilal Abdullawi. The work is presented by the corresponding author Mr. Soufiane BELAGOUNE. The abstract, the main role of optimal generator maintenance schedule (GMS) problem in power systems is to develop an optimal preventive maintenance schedule of power system generators. GMS should satisfy the load's power demand and crew constraints with ensuring the power system reliability at economical operation cost. In this paper, a more efficient optimization meta-heuristic approach based on Jaya algorithm for solving constrained and unconstrained optimization problems has been used for solving the GMS problem by minimizing a discrete evaluation function of a weighted sum of an objective function of the sum of squares of reserved generation and a penalty function for violations. The algorithm has been tested on the 21 units test system. It showed its effectiveness for solving the GMS problem and proved its reliability with best solutions as compared with other recent methods. Keywords: power systems, generators, preventive maintenance scheduling, meta-heuristic approach, discrete gyre optimization algorithm. The GMS problem is subjected to many constraints. In this paper, three constraints have been addressed. Maintenance window constraints, which consider an index MIT to be 1 if under maintenance and 0 if under no maintenance, where small t is time period index, big T is total planned horizon, small I is the generation number index, U is the total number of generators, Ui is outage duration for generator I, beta I is maintenance time interval. The resources allocation constraints take about ensuring that the required resources for performing the planned maintenance should not exceed the available resources. The resources can be special tools, labor force, spare parts. In our study, the labor force has been considered in the following equation, where the term ALFT is representing the available labor force at time t, and the term LFIT is representing the available labor force for maintaining unit I at time period t, load demand and reserve restrictions. The generated power should satisfy the load demand and the general reserve should be optimal and at minimum reserve level MRCT during the plant maintenance periods. The following equation, in the following equation, the first term is representing the maximum power generated by the substation. The second term is representing the generated power by the generators during the maintenance stage. The term LDT is representing the load demand at time period T. The term MRCT is representing the minimum reserve capacity at time period T. The GMS problem formulation. The reserve capacity. The reserve capacity at time period T during the planned time horizon should be optimal and at minimum reserve level MRCT as follows. MRCT is equal to the maximum power generated by the substation minus the generated power during maintenance stage minus the load demand at time period T. The objective function. The objective function f is equal to sigma and equal to the sum of the squares of the reserved generation from t equal to 1 to big T. In this paper, we consider a minimization problem. To minimize f, mean f is equal to mean sigma and equal to mean of the sum of the squares of the reserved generation from t equal to 1 to big T. The evaluation function and the test system. The evaluation function E is formulated as a weighted sum of the objective function sigma and the penalty function for violations. of the constraints alpha and beta as follows. E best is equal to mean of CR times sigma plus CM times alpha plus CL times beta, where CR and CM and CL are coefficients. CR is the reserve coefficient, and CM is the manpower coefficient, and CL is the load coefficient. The table 1 is representing the 21 units test system data, where in the first column we have the unit number index. In the second column we have the capacity in megawatt, the maximum capacity for each generator. And we have the allowed period for each generator to be maintained. And we have the outage in weeks for each generator in the allowed period. And we have the labor force required for each week to maintain each generator I. The discrete Jaya algorithm. The basics of discrete Jaya algorithm can be found in the reference below of Professor Venkata Rao, titled Jaya, a simple and new optimization algorithm for solving constrained and unconstrained optimization problems, in the International Journal of Industrial Engineering Computations. The flowchart of our work is in the following picture. Our results are compared with two recent papers. The first paper is of Professor Nordin Bali and Dr. Hilal Abdellawi, titled Optimal Generator Maintenance Scheduling Using a Hybrid Metaheuristic Approach, in the International Journal of Computational Intelligence and Applications. The second paper is of Professor Kishaf Dahal and Professor Shakpita, titled Generator Maintenance Scheduling in Power Systems Using Metaheuristic-Based Hybrid Approaches, in the well-known journal called Electric Power System Research. You see in table 4 the comparison results of the discrete Jaya algorithm with E-based results in reference number 1. The first method called genetic algorithm. The second, simulated annealing. The third is the end colony optimization. The fourth is the simulated annealing combined with end colony optimization. And DGA is the discrete Jaya algorithm. You see in stage 1 and stage 2 and stage 3. The discrete Jaya algorithm provides with amazing results of 135.7 in stage 1 and stage 2 and stage 3. The feasible solutions of the DGA is 100%. Table 5 represents the comparison results of discrete Jaya algorithm with E-based results in the reference number 17. The method 1 is called heuristic 1. The method 2 is equal heuristic 2. The third method is simulated annealing. The fourth method is genetic algorithm. The fifth method is the genetic algorithm combined with heuristic. And the sixth method is the genetic algorithm with simulated annealing hybrid. And the seventh method is the genetic algorithm combined with simulated annealing combined with heuristic method. And you see the DGA provides with an amazing results of average of best solutions of 135.7, and the best solution of the DGA is 133.09, as you see in the table number 5. The results are presented also in terms of figures. Figure number 2A represents the objective function curve decay. Figure number 2B represents the manpower against maintenance period per weeks. E best is equal 133.37. Figure number 3A represents the production in megawatt during maintenance period per weeks. And figure number 3B represents the maintenance scheduling per weeks. E best is equal 133.37. Conclusion. In this paper, a new metaheuristic method based on discrete Jaya algorithm has been presented for solving the GMS problem. It was compared with the performance of both genetic algorithm and colony optimization methods. The performance of the discrete gyre algorithm has been tested on the 21-unit benchmark test system. Discrete gyre algorithm showed its effectiveness and clearly it's more efficient than both genetic algorithm and colony optimization, and it provides with better results. As future work, new and recent meta-heuristic algorithms will be applied in solving the GMS problem in order to achieve better results. And thank you very much for watching our presentation.